Next speaker is Rhyno Strydom. He will be presenting a paper entitled Classify and Recognize Speech with Deep Neural Networks. With that said, I would like to hand it over to our speaker.
Thank you. I'll share my screen in a moment. Here we go. Can everybody see that?
Yes, it's clear.
Okay. So what the project is basically about is we acquire data from an automatic speech recognition system, ASR system, as Nuet referred to earlier, and analyze the text obtained from the ASR system to determine whether or not certain keywords of interest are mentioned falsely in broadcast news. So the main contributions that we show is the text obtained from the ASR system provides an interesting and important use case for these NLP techniques, and we demonstrate the relative capabilities of various NLP solutions, including embeddings and more traditional methods on such tasks in the multilingual South African context. What we investigate is TF-IDF, which is used as our baseline textual representation feature, Word2Vec, FastText, and Doc2Vec. We use both linear and nonlinear classification methods that explore the use of a logistic regression and deep neural network classifier. We also explore alternative methods of classification using only word embeddings and the cat-boost classifier trained on both the metadata and the output of the deep neural network trained on the textual features. So how to convert text to vectors. Previously, methods such as TF-IDF, which stands for Term Frequency Inverse Document Frequency, a way of expressing the importance of a word when considering the corpus as a whole, was used as a sort of way to summarize text data. The problem with these types of methods are that they fail to capture the regularities and linguistic structure within these languages, and they also disregard any word ordering or semantic meaning or syntactical relationship between words, which is quite important when considering any language. So in the last few years, there's been some promising results in regards to the performance relating to the success of deep learning methods and specifically word embeddings. So what is a word embedding? A word embedding is a way of representing words as continuous vectors, able to capture the semantic relationship between words in a relatively low dimensional space. So using the example shown, using the word king and man in conjunction with woman, the word queen can be arrived just by referring to their vectors. So how are word embeddings trained? Word embeddings are trained based on something called the distributional hypothesis. So basically what this says is words that appear in the same context share semantic meaning with each other. That is the basic premise of Word2Vec. FastText, a method similar to Word2Vec in that additionally to this is also enriches embeddings with words orthographic engrams. That meaning that morphologically rich languages such as German, where one word might refer to 3 different words in English when translated, can also be captured accurately. Doc2Vec works in a similar fashion to training word vectors, but instead of training vectors for individual word, it trains the fixed length paragraph representation for document as a whole by trying to predict words. So it's somewhat informal, it's trying to capture the context within these different documents, which can be sentences or paragraphs. So there are 2 methodologies mainly used. The one is they come in is Word2Vec, and the other one, okay, is Doc2Vec. They come in 2 flavors: continuous bag of words for Word2Vec and skipgram. Continuous bag of words basically maximizes the probability of the target word by looking at the context words here. Thus, given a set of words at the input, it aims to predict a specific word here at the output. Skipgram follows the inverse rule to this. The technique is designed to predict context given a specific target word. For Doc2Vec, we get similar types of methods, one called paragraph vectors for distributed memory, and the other called paragraph vectors for distributed bag of word. Paragraph vectors for distributed memory averages or concatenates the word and paragraph vectors to predict the next word in context. And that is learned and acts as a sort of a memory that remembers what is missing from the current context word here, which is summarized in this vector here, where continuous bag of words, on the other hand, forces the model to randomly predict sample words shown here and here from the paragraph at its input. This method, however, ignores word order and solely tries to capture some sort of context in a semi-supervised learning fashion. So how does the data look? So the speech text data that we analyze consists of 885,000 speech to text examples, of which 675,000 are examples of true positives and 210,000 examples of true negatives. Here I show how these examples are spread out through each language. So please note that this is a logarithmic curve, and English is by far the most dominant in comparison to all these languages. The reason for this is English being so dominant in news broadcasting and also commonly used through advertisements and just general broadcasting stations as a whole. So how did I, extract the data? What did I do before I started training these embeddings and building these classifiers? So before I did any of that, I had a pre-processing pipeline, which basically tries and extracts the JSON files that I get from the ASR system, normalizes the text by lowercasing the words, and removing any unnecessary stop words, lemmatizing it, identifying common phrases, then extracting different window sizes around specific keywords of interest. The result is a corpus that looks something like this. For each window size, I get a different word count and a different vocabulary size, where, for example, a word ESCOM is recognized, a word is captured in a way similar to what is shown in this example. So for a window size of 5, and for the example ESCOM, this is typically how that would look in one of these examples. The data is split into a training, validation, and test set by randomly splitting the data according to how frequently specific keywords appear in the corpus. Training on 80% of it and using 10% of it for validation and another 10% for just testing. So the classifiers that I spoke of or mentioned earlier, logistic regression, deep neural networks, and the CatBoost classifier. Doc2Vec, Word2Vec, FastText, and TF-IDF are investigated using logistic regression, a linear classifier, and a one-layer feed-forward neural network, a non-linear classifier with varying capacity. The metadata associated with the text is also used to train the CatBoost classifier, features including the broadcast station name, the keyword of interest, the language, and time of day. Output of the deep neural network is also used as an additional input feature. To mitigate the effect of the class imbalance, class-weighted loss is used to as the data set is unbalanced, giving higher weight to where less examples are present and less weight to the loss where more examples are present in the corpus. Another technique that is explored is a technique I coined average cosine similarity method. The basic premise here is that keywords that are identified as false positives will surround itself by similarly incorrect words that have nothing to do with the actual keywords. So what we do is we add a flag to specific keywords, train an embedding for it, and find the average cosine similarity between both examples, basically trying to identify if the word Disney was mentioned in an Afrikaans word because it will surround itself with a similarly sounding Afrikaans word, or English, where it will surround itself with the correct English words, just by comparing the cosine similarity and training in an unsupervised or semi-supervised fashion. So the metric used for evaluation is the Cohen-Kappa statistic, is used to compare the various classifiers, which is sort of a measure of the iterated agreement between categorical items. For the CatBoost classifier, the shop values are used to evaluate feature importance. So just to show exactly which features are most relevant for the classifier during a specific prediction. To give some intuition behind this, This is just a basic diagram for the classification scale that is used for the cone, evaluating the results of the cone kappa. And it will become more apparent as I go into the next slide. So the results. Okay, what I basically saw is that using FastX and Word2Vec algorithms for the logistic regression classifier obviously didn't do as well as for the deep neural classifier. However, the difference between using that and TF-IDF is more prominent, and even more prominent so using document vectors as shown in the green here. So here you can see a vast difference in how the document vectors cone kappa score here and here for the deep neural network of 400 with 400 nodes. Also, for a window size of 11 and window size of 21, proved superior for both the Word2Vec and FastX cases of training the deep neural network. But TF-IDF still prevailed and dominated using a deep neural network with 400. The other technique that was explored, the average cosine similarity method, performed well, but still better than the logistic regression examples, like if you just look here and some of the examples here. Although the continuous bag of words method didn't perform as well and significantly actually degraded. So skipgram actually worked better in these cases. For all these cases, however, the baseline cat-boost classifier still performed the best. However, adding TF-IDF as an additional feature to the input of the cat-boost classifier did not enhance performance and actually degraded it due to overfitting, which should also become apparent in the next slide. We reserved the test results for only the best results that were obtained here. So that was for the cat-boost classifier, the baseline one, only using the metadata and the TF-IDF shown here, and with the Word2Vec shown here. So in this slide, I basically just show the relative importance of each feature. So for the cat-boost classifier, the target word trained and broadcast station name trained was some of the most important features that was used to for the model to make predictions. However, like I said, adding TF-IDF actually degraded performance and caused the cat-boost classifier to solely overfit on this specific feature. This is shown by the Y-predict, which is the output of the deep neural network. However, adding a weaker classifier like let's say Word2Vec with a deep neural network enhanced performance slightly, with the main feature still being the predicted value from the neural network, however, not overshadowing some of the other important features such as target word trained and broadcast station name trained upon. In conclusion, applying the TF-IDF as a textual representation with a neural network outperformed all other embedding-based methods. Considering the output of the deep neural network using TF-IDF and cat-boost classifier as an additional feature to the cat-boost classifier caused the classifier to overfit on this feature and actually caused the model to do worse. Word2Vec using a slightly worse, less a model that is slightly less well using deep neural networks performs slightly better as an additional input feature to the classifier, but still didn't improve in the baseline results of the classifier in a significant way. So, questions?
Thank you.